So, worksheet for my questions on molecular structures 1A, covalent compounds, simple Lewis structures, some GCSE material in here, but always important to check that you know the fundamentals, the absolute fundamentals about things like identifying what an ionic compound is, naming covalent compounds, and so on. So we'll start nice and easily, and I will spend a bit of time on this first question and also the third question, just to make sure everybody's on the same page. So the correct name of N2O3 is, well, this is a covalent compound because N and O are both non-metals. The way that we name covalent compounds is for each atom that's in there, we put a prefix and then the name of the atom, and the order of the atoms is based upon their position on the periodic table. If there is an atom that's further to the left, that one goes first. If they're in the same group, the first one is the one lower down. For the first atom, we use its name. For the second atom, we turn it into its ide form. And of course, the prefix for each type of atom refers to how many of that type of atom. So we'll look at the periodic table here. We've got nitrogen and oxygen. There's nitrogen, there's oxygen, so nitrogen is obviously to the left, so it's going to be something to do with a nitrogen oxide. Okay, the oxygen, the one on the right, turns into its oxide form. How many do we have? Well, we have 2 nitrogens, so that's di, 3 oxygens, tri. So dinitrogen trioxide. It is, after you've done it a couple of times, it should be absolutely intuitive and straightforward. Second one, tetrasulfur dinitride decomposes explosively when heated. Who really cares in this context? What's its formula? Well, we've obviously got sulfur and nitrogen. Tetra is 4, di is 2, so it will be S4N2 again. Which set contains no ionically bonded species? NH4NO3, NH3, XeF2, AlO3, blah, blah, you can read it for yourselves. So anyway, ionically bonded species traditionally are between metals and non-metals. So let's eliminate those. So we have here sodium with a whole bunch of non-metals, sodium with a non-metal. But then you can also get ionic species that look like they're made up of a whole bunch of non-metals, but that's because they're made up of polyatomic ions. Very, very important that you're able to recognize all polyatomic ions. So let's see which ones have polyatomic ions here. NH4, really the first, the most important polyatomic cation, but then NO3 is the anion. Here again, NH4 is the cation, Br- is the anion. So the only one here that doesn't have an ionically bonded species is the last one. Let's make sure that we got boron, metalloid, non-metal, metalloid, non-metal, non-metal, non-metal. So that makes nice sense that those are not ionically bonded. They're all covalently bonded. Now we're moving to dot and cross diagrams, which I resolutely refuse to call them because they're stupid. They are Lewis structures. I feel at this stage of your education you should be able to do it properly as Lewis structures, as just dot diagrams, none of these crosses in there. I think I talked about that in the movie quite extensively. So I'm not going to do dot and cross diagrams. I'm going to do Lewis structures. It's relatively easy to go from Lewis structures back to dot and cross diagrams if your teachers or whatever insist you do so. Anyway, Lewis structure of Sf2. So the way I like to draw Lewis structures is I start off with common sense. I just look at all of the different types of non-metallic atom or metalloid atom, and we say, well, these are going to make as many bonds as they need electrons to get up to 8 if they're going to be sensible. There are lots of exceptions to common sense, but if something follows common sense, it's much, much, much easier. So Sf2, well, S is in the same group as oxygen, so it wants 2 bonds. F is in the same group as chlorine, so it wants 1 bond. Thus you put them together and you're going to have the sulfur making 2 bonds, the fluorine making 1 bond each. The lone pairs, rather important of course when we get further into consideration of structures. The sulfur starts with 6 valence electrons, just like oxygen, so it wants 2 more. So it will use 2 of those 6 to make bonds, leaving it with 4 left over as lone pairs. The fluorine, just like chlorine, got 7 valence electrons, uses 1 to make the bond when it's common sense, leaving it with 6. or 3 lone pairs. So we look at the structure of Sf2 and we see there are 2 single bonds and 1, 2, 3, 4, 5, 6, 7, 8 lone pairs. Interestingly, there are quite a lot of compounds between sulfur and fluorine, and all of them except Sf2 do not follow common sense, but the only one that doesn't occur, or if it does occur it is just fleeting, is Sf2. Kind of an interesting little phenomenon there. Question 5, most reasonable Lewis structure for NOCl. Well, we've got them right there. Nitrogen wants to make 3 bonds, so we'll have a lone pair left. Oxygen, just like sulfur, wants to make 2 bonds, so 2 lone pairs. Chlorine, just like fluorine, 1 bond, 3 lone pairs. Best way to put these together is to take the atom that wants 3 bonds, have it make 2 bonds to the atom that wants 2 bonds, and 1 bond to the atom that wants 1 bond. So therefore, there is the structure. Notice that the formula does not give you any clues about the structure at all. Okay, so something very, very important to remember is a lot of times the formula is written in some weird convention that does not tell you about the structure. Question 6, which molecule contains only 2 unshared pairs of electrons? All of these but one obey common sense. H2O, oxygen, 2 bonds, 2 lone pairs. Hydrogen, of course, never more than 1 bond. NH3, nitrogen, 3 bonds, 1 lone pair. Hydrogen, never more than 1 bond. BeCl2 is a bit of a silly one. Beryllium, of course, has actually a metal, even though it exhibits quite a lot of metalloid type features in its structures. It only has 2 electrons, and so if it's going to make covalent bonds, it can only make 2 bonds and not have any lone pairs. The only time you see something like BeCl2 is in very high temperatures in the gas phase. Otherwise, it will link up with other BeCl2 moieties to make bigger structures that give the beryllium more electrons. But anyway, BeCl2, an exception to the common sense idea, because there is no choice what to do here. There are those, and occasionally I'll argue it myself, who will actually put double bonds in between the beryllium and the chlorine, but now you're just starting to get silly about things. Anyway, finally, DO2, each oxygen wants 2 bonds, so you have to have a double bond. Thus water, only one with 2 unshared pairs of electrons. Which following molecules contains exactly 2 lone pairs? Again, all of these are going to follow common sense in some form or other. C2H4, bond the 2 carbons together. You've got enough hydrogens to give them 2 more bonds each, so there's 1 bond on each carbon lacking. Thus the way they will make things happy is to make a double bond, so we have no lone pairs there. CH4O, where you've got to bond the carbon and the oxygen. When you do that, you've got space for 1, 2, 3, 4 hydrogens, so super, there is a methanol right there. 2 lone pairs, so that looks pretty good. But remember, always keep checking in multiple choice scenarios. OCl2, oxygen wants 2 bonds, chlorine wants 1 bond each, so there's your OCl2, and it's got a nice whopping total of 8 lone pairs. CCl2F2, carbon wants 4, each of those halogens wants 1, so very easy to pop a halogen on the end of each bond, giving us a total of 12 lone pairs. And Cl2, each chlorine wants 1 bond, so you're just going to have a single bond between the 2 chlorines, and 6 lone pairs. I'm going through these relatively quickly because, quite frankly, that's not a good way to go through them slowly. But the way to draw these Lewis structures, dot and cross diagrams if you insist, is to just practice the things. Now, every single one of these, I've drawn a line where your dot and cross would have a dot and a cross, indicating, of course, that that line is a bond between 2 atoms. Each atom has contributed formally 1 electron into the bond.